Good afternoon. My name is Dan Funk. I'm in the Office of Nuclear Energy, the Advanced Modeling and Simulation Office. I work for Trevor Cook, who is the Director of NE41, and for Shane Johnson, who is the Deputy Assistant Secretary for the Office of Science and Technology Innovation, NE4. Over the years, I have learned to not underestimate the ability of an intelligent, highly educated audience to humble a presenter. So I'm sure that you are able and probably will come up with questions I cannot answer, but we will get answers to you one way or another. Similarly, it is crucial that we feds not underestimate the pitfalls and perils that can trip up even the best run programs. I'm reminded of an old story of the man who owned a Mastiff, a most powerful and intimidating dog, of which he was immensely proud. Well, one day when he was out walking his huge, ferocious dog in the park, he saw another man approaching with his own little yellow dog on a leash. It was clear that they were going to pass right by each other. But the Mastiff's owner was not worried about his dog in the least. His concern was for the little yellow dog. As his big Mastiff became more and more agitated, growling and snarling horribly, wanting to tear that little dog to pieces, he yelled out for the other man to be careful and to get his little dog away from there. Too late. The huge Mastiff broke his leash and rushed at the little dog. And just as he reached him, the little yellow dog's mouth opened wide and snapped down on the Mastiff, cutting him in half. And of course, the shocked beyond belief, the owner of the Mastiff said, all he could stammer was, "What in heaven's name kind of dog is that?" And the other fellow replied, "Oh, him? Well, before I cut off his tail and painted him yellow, he was an alligator." But I do not need to tell you about all of that. You folks are well acquainted with the complexities and technical dangers, the alligators, as it were, that can keep even the most well-directed and well-funded research from meeting its goals. So the theme of this is your job, should you decide to accept it, is to help us find and avoid those alligators in whatever guise they might come. This may be a rerun for many of you, but I ask your forbearance as I highlight the context and overall structure of Neams for those who may not be as familiar with our program as you are. It is widely recognized that advanced modeling and simulation capabilities applied in concert with experimentation and theory enhance and speed scientific discovery. The more predictive, mechanistic, and usable these advanced capabilities are, the more pronounced the effect. Thus, modeling and simulation are now, and have been, a part of R&D. Neams isn't doing that R&D, but rather developing the new modeling and simulation capabilities to be used by others in that R&D. The Neams program has emerged from an earlier evolutionary period as a compact, robust, highly focused effort. But it is not enough to be compact, robust, and highly focused. It must be something that is driven by and toward a clear mission and a value proposition supported by solid, stakeholder-driven requirements and technical merit. And so, there we have it. As you can see from this slide, our goal is to produce capabilities that can be used to gain insights not obtainable by experimentation alone. And that these capabilities are to be delivered as multiple tool sets integrated into a Neams toolkit that can be used separately, in combination, or all together. And these are our products. Neams is organized into two product lines. The fuels product line, the reactor product line, and then both these lines support the development of Relapse 7. For the fuels product line, the goal is to be able to apply the fuels product line tool set in the Neams toolkit to several fuels R&D areas: advanced fuel designs, accident-tolerant fuels research, and capabilities that can be extended to simulate behavior of used fuel in long-term storage. The focus is to develop mechanistic, truly predictive computational capabilities that would have both near-term and long-term impact. The context of our effort in the fuels area is one that involves multiphysics, multi-scale. And by multiphysics, we would mean fully coupled, nonlinear thermomechanics, mass transport, chemistry, neutronics, and thermal hydraulics. Multi-scale, there's a multi-space scale and multi-time scale. Multi-space scale, its important physics operate at the level of the microstructure. And we need real predictions at the engineering scale. Multi-time scale because we have to deal with long, steady operations, short power ramps, and rapid transients. Okay, what you see here is a graphic that depicts the relationship between marmot, bison, and moose, and roughly how they work together from a very high level. And the idea is that in the lower length scales, the atomistic to mesoscale material model development, we develop these tools. They then can be integrated into bison, which gives us an engineering scale fuel performance capability. And that these applications run on Moose, which is multi-physics, object-oriented simulation environment. It's a simulation framework that enables rapid development of finite element based applications. Marmot itself predicts the coevolution of microstructure and properties due to applied load, temperature gradients, and radiation damage. And the technique there is primarily a phase field coupled with large deformation, solid mechanics, and heat conduction, solved with implicit finite elements using Moose. And some of the physical models that we derive from that are the grain growth, grain boundary migration, bubble growth and migration, species redistribution, stress effects on evolution, and crystal plasticity. Looking at this another way, the atomistic and marmot simulations are used to develop new predictive models. Shown there are primarily the four areas: the fission gas release, the thermal conductivity, fuel relocation and restructuring, and fuel fracture. One example that helps you helps us explain how this works is we know that various methods are employed at different scales to investigate different stages of fission gas release. So, for instance, the density field theory and molecular dynamics shown there or how we would analyze and understand diffusion of individual fission gas atoms in bulk UO2, plus nucleation growth and resolution of intergranular bubbles. And then, using molecular dynamics and kinetic Monte Carlo, we would deal with xenon segregation, clustering, and bubble nucleation. And then bubble growth and coalescence is handled with field phase modeling. And finally, percolation analysis it helps us understand percolation in polycrystalline networks. Ultimately, we want to end up with a tool, Bison, that can be used for predicting fuel performance at the engineering scale. So what we have in summary is what you see here. It's based on a solution method that involves implicit finite element solutions of coupled thermomechanics and species diffusion equations using the Moose framework through multi-physics constitutive models, which help us to describe and simulate large deformation mechanics, which is plasticity, creep, and cracking, and thermal expansion, and densification, and radiation effects such as swelling and thermal conductivity. And some of the current Bison capabilities are shown here. Some of these slides we will not go through in detail, but I encourage you to look at them later, and if it prompts any questions or further inquiry, please make that, and we will have our technical people available to get you the answers you need to fully understand technical details that you might need to know. And in the fuels product line, validation, which is the theme, primary theme of our scope in this year's call, and it represents one of our areas of greatest need. And so you see here some points made on validation of Bison to date. Bison and associated software is supported by extensive regression testing. We've completed about 20 LWR oxide fuel cases, about 13 triso fuel cases. But many, many more are needed. And one of the major emphases for fiscal year 14 are the FUMEX 2 and 3 priority cases. The overall approach the overall effort is to develop a systematic approach to frequently run all cases and update documentation continuously. We also are using Dakota and Raven for sensitivity analysis and UQ studies. In this area, there may be a lot of details and other information that could be helpful to you. So I encourage you to inquire and pursue that, because there are some documents, and we also have some folks that you can talk to that can answer your questions and give you information that might give you some insights on what kind of proposals we're looking for, what kind of proposals you might be able to come up with. And finally, in the fuels area, Bison is being used. And as you can see, we've got a short list here, and that use is widespread and growing. We also have users in industry and international users as well. Of course, Bison, we had a code release, version 1.0, about a month ago. We've also released 3 manuals that I think you should perhaps look at. There's the Bison Theory Manual, there's the Bison User Manual, and the Bison Assessment Manual. And there are also a list that we can get to you of journal and conference papers from 2013, which might be helpful. In the Neams reactor product line, that toolkit, with its 3D, high-fidelity, coupled physics, and multi-scale simulation capabilities, enables the design of future nuclear power stations and reactor cores. Here again, the goal is to make it useful, usable, and used. Now, the development roadmap is here. You can see this: neutronics, thermal mechanics, fluid mechanics, structural mechanics, system response, and you can see all these different areas. So what we're doing in those areas is represented in this slide, where you can see that the applications, the codes, and the frameworks are represented. They'll give you a picture of how this toolkit is being assembled. In addition, this slide right here shows a little more detail of how the components are assembled and interface. Again, there is a lot of detail that we cannot go through right now because of the constraints on time. However, this should give you a nice roadmap to understand what we're doing and ask further questions as needed. So the approach here in the reactor product line to make this an innovative tool that's truly an advanced capability, we need to make it useful, make it robust, make it predictive, make it accurate, make it easy to use. Making it useful by building on past success. Making it applicable to a wide range of reactor types. And making it possible to apply a desired level of fidelity in regions of varying interest. And to make it able to be used as a complete multi-physics package or as individual modules. Make it robust, modular construction, object-oriented programming, rigorous version control, automated verification of all components. Make it predictive. High-fidelity unstructured mesh neutronics, high-fidelity CFD tools for reactor problems, high-fidelity structural analysis tools, and next-generation reactor systems analysis capability. Making it accurate. First-of-a-kind, high-order mesh-based data transfer capability for coupled multi-physics, and enable a variety of iteration schemes. Make it easy to use. And you can see there some of the points that underlie that. One of the solution examples comes from Texas A&M. They're using NEC 5000 to simulate pebble beds. Another example is from industry. It's a reactor design example, as you can see, concerning the pressure drop across multiple components. Here again, reactor product line validation. And you can see the approach we're using there. Obviously, we can only validate these tools to a certain extent. We can't possibly validate them for every possible use. So there are a lot of application-specific validation efforts that will be needed. And we invite help on that as well, or at least scientific information that would be useful to users. So you can see both from the fuels product line validation and the reactor product line validation, you can see what we're doing here and fit your inquiries into that framework. Again, the reactor product line is used, and this slide just gives you a good idea of how many users there are and what is being used. So, in summary, you have here the NEAP work scope description, which you already have from other sources. You also have these links, and I encourage you to pursue those, both the program plan and the VMV plan. And since this is a VMV-related scope, I think that would be important for you to look at. And if there's any questions about these particular bullets or any of the other information that I've provided here, please ask now. And if you have questions later, that's fine as well. So that's it.
Okay, we have one question. It's, can you post links to the Bison documents you mentioned? I'm assuming they're saying on NEUP.gov.
I believe the answer to that is yes, but I will have to confirm that. Certainly would like to make them available to as many people as easily as possible. So thank you for that question.